Okay, so let's try this. All right, so our hypotheses. Okay, we've got to look at the statement here, and it says, is this evidence that the average of the population is not $46? Okay, so from there we can figure out our null and our alternative hypothesis. Okay, what is my null hypothesis?
46.
It's not. It's mu equals 46. Okay, so please, all right, please be careful. Okay, because we are asking, is it evidence that it's not 46? We're not asking about the sample. We know my sample is 4350. Okay, we're asking, is the population mean 46? Notice I'm using mu, not p. It's not x bar, okay, and it's not 46 all by itself. The null hypothesis is that mu equals 46. All right, so those are all very important points that if we write something other than this, it's not correct. The alternative would then be mu
not equal to
does not equal 46. Now, if this said, is this evidence that the population mean that the average of the population is less than 46? Then I would put a less than sign here. What is my standard error?
1.44.
Okay, my standard error is s over the square root of n, 7.23 divided by the square root of 25, and you guys told me that is what?
1.44. I just got
1.446, is that right?
I just got 1.44.
Let me just check. 7.23 divided by 5. Yeah, 1.446. Good. What is the test statistic? So this is my observed minus what I expected divided by the standard error, my test statistic. So this is, I observed a mean of 4350, and I'm expecting $46. Okay? So I'm making a little bit less money than what I'm expecting. Is this a big deal or not? So 1.446 is my standard error. And I get 1.729. Or negative 1.729. Okay? So my machines are making less than what I expected, but is this a big deal or not? Is it within the norm of just different things? Okay. So my degrees of freedom is 24 degrees of freedom, n minus 1, so I have 24 degrees of freedom. And I go to the row in the table with 24 degrees of freedom, and I'm looking up 1.729. I just ignore the negative sign, and I go to 24 degrees of freedom. Okay. And so I have 1.318, 1.711, and 2.064. The number I have is 1.729. And that is in between the number for 0.05 and 0.025. Is that okay? So the area in my tail, if I go to one of the tails, the area in my tail is between 0.025 is less than my tail, less than 0.05. Okay? And the same over here. Same with this tail. Okay? So the total in my tail area, so the total p-value, which is in both tails, is going to be between what?
100 and 0.550?
0.05 and 0.10. Okay, so 5% and 10%. Okay.
I have a quick question.
Yes.
And I think I get it. I just want to hear you explain it. we have 4 degrees of freedom because the number fell in between the,
No, my degrees of freedom is n minus 1, so I have 24.
right?
So I have 25 in my sample, I do n minus 1, and I use 24 degrees of freedom.
Okay, so it was 24 degrees.
24 degrees of freedom. And my tail area is between 0.025 and 0.05. But my p-value, okay, because I have a not equal to sign, I double the tail for the p-value, okay? Double the tail for the p-value. Which is what I'm doing here. I'm doubling my tail to get 5% and 10%. So my p-value is between 5% and 10%. And that's only because I have a not equal sign in my alternative. If I have a less than sign, I just leave it as between 0.025 and 0.05. Okay?
What's the greater sign?
If you have a greater than sign, same thing. You just leave it as between 0.025 and 0.05. So my p-value is between 5% and 10%.
So that not equal to is always an indication for us to know that we have two tails.
That we have 2 tails, exactly. That is the indicator, the not equal sign. Yeah.
So basically, you just find out what numbers you're in between, and then find what numbers those equate to the
Exactly.
value, and then double it.
You double it only if there's a not equal sign, okay? If it's 2 tails. All right, so what conclusion do we make? Well, this requires us to choose an alpha. So if I didn't specify an alpha, so let's assume alpha was 5%. So is my p-value bigger or smaller than alpha? It's bigger than alpha, so my p-value is bigger than alpha. Oops. So what is my conclusion?
We accept it.
We do not reject. Don't say accept. We say we do not reject the null hypothesis. And that means what? Is this evidence that the average of the population is not $46? No, it is not evidence. So the fact that our 25 vending machines only made us $43.50 is not evidence that the average is not $46. Okay. The data is not evidence that the average is different than $46. Okay. How's that? Yay? Not really? Okay. We'll practice this, okay? You guys have this in your notes, okay? Go through it and practice this. You'll see, you might see something like this that's similar on the quiz. It might be a little bit different. Maybe it uses proportions, but so study, hypothesis tests for proportions, hypothesis tests for means, and confidence intervals. And there's one more confidence interval I gotta teach you guys. Yes?
So expected is $43.50 and observed is $46.
No. Expected is 46.
Expected is 46.
What we observed is 43.50. Okay? So basically the average from our 25 machines is 43.50. Okay? That will always, whatever you get from your sample, that's your observed. That will never be your expected. Okay? Never be your expected. I really like teaching, but It's hard talking up here for 3 hours. Okay, let's talk about confidence intervals for means of 2 samples. I wonder if teachers ever get vocal notes. It's only from singing, right? After that movie. Okay. Confidence intervals for means of 2 samples. So now we are dealing with 2 samples and we're comparing the means. And we want to see what this says about the respective populations. Confidence intervals for 1 sample was we looked at 1 mean. And we said, what does this say about the population? Here we're going to look at 2 samples and their means. And we're going to ask, what does this say about their respective populations? What do the means of 2 samples about the respective populations? All right, so sample 1, what are the bits of information we need when we talk about a sample and we're dealing with means?
You know the
Size of the sample. The, what else about the sample? Not the proportion, because we're dealing with a numeric variable. So we need the mean of the sample and the standard deviation of the sample. Okay? Now I put a 1 next to all of these to indicate this is the size, the mean, and the standard deviation of sample number 1.
Is that a Y one or mu one?
You know, X bar 1, you know.
Okay.
In my Stat 13 class, the textbook uses Y.
Okay.
And so I was writing similar stuff up on the board. Sometimes I get confused. It's the same thing, but so as we remain consistent, we use X bar, okay? And then for sample 2, it's the same thing, N, X bar, and S, but to indicate that it's coming from sample 2, I put a little 2 next to each of these subscripts. And so now we make the confidence interval. And here we want to make a confidence interval for, when we made it for 1 sample, it was for the population mean mu, right? Now that we have 2 samples, we have 2 populations, and each population has their own respective mean mu. So we are going to make a confidence interval for the difference between mu1 and mu2. Okay. So we're asking, do the respective populations, do they have the same mean, or are their means different? That's what we're asking here. So our estimate, what is our estimate of the difference between the means of the populations? Based on our sample data. X bar 1 minus X bar 2, right? This would serve as an estimate of the true value, right? We don't have the true value mu, so we're just going to plug in the means from our samples to kind of estimate it. And we're going to go plus or minus, what, the margin of error? And what do you think our margin of error is?
S1 minus S2.
Okay, no, we're going to do T star times the standard error. Okay. This part looks familiar, right? It's just like before, okay? Alright. T star times the standard error, this is still, we still call this the margin of error. Alright, this is still called the critical value, and this is still called the standard error. Okay? This is the change. The difference here is that the formula for the standard error just got ugly. Okay? And there's nothing we can do. It's just an ugly formula for the standard error, and we're just going to plug numbers into it and get an answer. Okay? So the standard deviation of group 1 squared divided by n1 plus the standard deviation of group 2 squared divided by n2, the size of group 2, take the square root of the whole thing. Okay. And this is the standard error for confidence intervals for means of 2 samples. Okay? So we've seen several different standard errors. We've seen a standard error for a confidence interval for one proportion. We've seen a standard error for a confidence interval for one mean. Okay, and now we have a standard error for a confidence interval for 2 means. Okay, or 2 samples. Okay, so we've got a bunch of different standard errors, and we've got to keep track of all of these and make sure we use the right one. But the overall idea of a confidence interval remains the same. We put something in the middle, which is the estimate of whatever we're going for, and we go plus or minus the margin of error. And the margin of error is some critical value times the standard error. So that's that. Okay, now to select our T star, we need to know the degrees of freedom. So the degrees of freedom is n minus 1, okay, but we have 2 n's. We've got an n for sample 1, and we have an n for sample 2. So we are going to use the n of the smaller sample, okay? So whichever sample has a smaller n, we're going to use that as the n minus 1. So if we have sample 1 is 8 people and sample 2 is 30 people, we're going to use 8 minus 1, 7 degrees of freedom. Does that make sense? So we use the n of the sample with fewer items or people. Fewer items. And other than that, that's it. Confidence interval for a difference between means.
We squared this before we divided by the n, right?
Yes, you do s1 squared divided by n1. s2 squared divided by n2. Okay? Should we make sure we know how to use our calculators okay, or do you think we're okay? Try an example here? All right, let's try an example here. Okay, so let's say sample 1, let's say we're dealing with men, and sample 2, women. And let's say we took the heights of 15 men and 20 women. X bar of the men, let's say average of 70 inches, and X bar of the women, let's say was 65 inches. Let's say standard deviation of group 1 was 3.5 inches, and the standard deviation of group 2, let's say was 3 inches. Okay, so I'm going to say make a 95% confidence interval for mu1 minus mu2. And you have the equation right up there. You know how to find degrees of freedom, and you know how to find the standard error. Okay? Is this okay? You guys can do this?
Is it 35 or 3.5?
3.5. Standard deviation of 35 would be very, very, very big. Get this for an answer? No?
Wait, not done. Not yet, not
Yes?
yet.
Maybe?
Not yet.
Low 2.59 to a high of 7.41. Yeah? No?
Yeah, no done.
Okay, let's see what happens. All right. X1 minus X2 bar. X1 bar is 70. X2 bar is 65. Plus or minus. Okay? What is my degrees of freedom? 14 degrees of freedom. 95% confidence. What's the number I'm going to use?
2.145.
2.145, right?
Yeah.
Okay, plus or minus 2.145. All I'm doing is plugging in numbers from here. And what's my standard error? Okay, well, we use this thing, yeah? And so I do 3.5 squared divided by 15 plus 3 squared divided by 20, and I take the square root of that whole thing.
That's 1.125.
And I get 1.125, I think. But
Yeah.
let's just 3.5 squared divided by 15 plus 3 squared over 20. If you have a fancy calculator, you can just punch it all in one go, and you get 1.125. Fantastic. Okay. Times.
Oh, so that's the T
No.
value you have to put in?
No, you said you had a fancy calculator.
Yeah. So all you have to do, okay, you get two. So you're gonna hit 3.5, and there's a square button. Okay. Probably on your calculator, it probably looks like this, x2, and then you're gonna hit the divide key, 15 plus 3 square button, divide key 20 equals, okay? And when you do that, you're gonna get like 1.26 something, and then you do square root button, answer, and you should get 1.125. Try that out. Yeah, it worked. All right. Yes.
I'm just confused about, I see 2.145 and I see that the
DF is 14.
Yeah, it's 14, but how did you know to go to 2.1?
Because I'm doing a 95% confidence interval. So at the top it says 95% confidence. Okay, so I have that. So 2.145 times my answer gives me
7.41. 413.
so I get 2.41, right? And 70 minus 65 is 5. So
Oh, you multiply.
2.145 times 1.125 gives me 2.41. Yeah, you can do 4. I just went to 2. It doesn't matter. It doesn't. Okay. I'm feeling like 2 today, alright? Sorry. Okay. So I have 5 plus or minus 2.41. So on the high end I do 5 plus 2.41 and I get 7.41. And on the low end I do 5 minus 2.41 and I get 2.59.
Isn't it 7.413? Would we get marked off if we did 4?
Okay, yeah, you can keep the third decimal or
Okay,
whatever.
fine,
I'm not
okay.
gonna mark you off for that, okay?
Awesome.
You know, for means, I usually keep fewer decimals. For proportions, it's usually more important to keep more decimals for proportions. Okay? That's the rule of thumb. Keep more decimals when you're dealing with proportions. For means, fewer decimals is usually okay. All right, so what's our interpretation? We would say I am 95% confident that what? Remember, here we're dealing with the average height of a man and the average height of a woman. So, okay, so it used to be, you know, I'm 95% confident that the average height of a man is between this and this, or something like that. But here, now we're dealing for mu1 minus mu2, okay? So what this represents, it's the average height difference, or the height difference between the average man and the average woman. It's the height difference between the average man and the average woman. So I would say I am 95% confident that the height of a man which is mu1, that the average height of a man is between 2.59 inches and 7.41 inches taller than the average height of a woman, which is mu2. Okay? So I was saying that the average height of a man is between 2.59 and 7.41 inches taller than the average height of a woman. Okay? And does that make sense?
Mm-hmm.
Okay? And it does, right? So, I mean, of course, if we pick any individual male, he might be taller or shorter than any other random woman that we might pick. But overall, on average, the average height of a man is somewhere between 2.59 and 7.41 inches taller than the average height of a woman. So do we have evidence that the average height of a man is taller than the average height of a woman?
Yes.
Yes, yes, okay? Because our entire confidence interval is entirely positive, right?
Mm-hmm.
It's the average height of a man is between basically 2.5 inches to 7.5 inches-ish, okay? I'm just rounding up to the nearest half inch, okay?
Mm-hmm.
So the average height of a man is between 2.5 inches and 7.5 inches taller than the average height of a woman, okay? And so that seems, that is evidence that there is a difference between the heights, okay? So we would say, because 0 is not in my interval of possibility, okay? Meaning, if 0 were in my interval, that would mean it's possible for there to be no difference between the average heights, okay? But because 0 is not in the interval, I have evidence that the average height, or that there is a difference between the average height of a man and the average height of a woman, okay? Or that there's a difference between, I'll just say the mean heights. Because 0 is not in the interval. I have evidence that there is a difference between the mean heights. On the other hand, if 0 were in the interval, what would my interval have to look like? Yeah, for 0 to be in the interval, I would have to go from negative something to positive something, okay? So if my interval went from negative something to positive something, then 0 is a plausible value for the difference between means, and then I would say I don't have evidence of a difference between the means. Okay. So I want to write that somewhere. So if, our interval goes from negative something to positive, then 0 is in our interval. Okay. And 0 would be a plausible value for mu1 minus mu2, okay, which between the means. So we would not have evidence. So we would not have evidence that there is a difference between the means. Okay. So probably something like, rather than heights, if we measured blood pressure of men and women. Okay? Is there a difference between the blood pressure? Okay, with a sample of 15 men and 20 women, you probably won't have evidence that there's a difference between the average blood pressure of a man and the average blood pressure of a woman. Okay? Maybe if you had tons and tons of people, you might find an overall difference, but probably with a sample size of 20 people and 15 people, it won't be evidence that there's a difference between the averages. Okay, and it would probably go from negative something to positive something. Is that good? All right. So the last thing that we're going to cover today is the last new thing, and we'll go. I'll let you guys go, and that's going to be pretty much the heavy chunk, heavy bits of what we need to learn. Okay, and then next week I'm going to go more in depth in all of this stuff we've covered. And your homework might touch on some of this, okay? But we'll talk about it next week. Okay, so now we have hypothesis tests, okay? This is our favorite thing, right? Confidence intervals and hypothesis tests. Okay. Hypothesis tests, now it's going to be for numeric variables, or so for 2 samples, and we're dealing with means. Okay. And again, because we're dealing with 2 samples, our data will have these bits of information. The size of sample 1, the average of sample 1, standard deviation of sample 1. Size of sample 2, average of sample 2, standard deviation of sample 2. And this is the hypothesis test for 2 samples, and we're dealing with means. So far, so good? All right. What's the first thing we may do in a hypothesis test? We make hypotheses, or we state our hypothesis. So here, our hypothesis, our null and our alternative hypothesis. The null hypothesis is going to be that the 2 means are the same. So I would write mu1 equals mu2, okay? Sometimes we can also write it this way. These 2 things are saying the exact same thing. One says the means are the same, and the other says the difference between the means, there is no difference between the means, okay? We're saying the same thing, right?
Yeah.
Just 2 ways of saying the same thing. This is always going to be, whenever we're dealing with a hypothesis test for 2 sample means, your null hypothesis will always be this or this, and either one is perfectly valid. Okay, this is always the null hypothesis for you. Okay? And what do you think the alternative then is? Yeah, mu1 does not equal mu2, or depending, you can have greater than or less than, and then likewise, that the difference doesn't equal 0 or greater than or less than. Okay, depending on how the question is phrased. Okay, this is going to look very similar to a hypothesis test for a difference between 2 proportions. Okay, we're going to make a test statistic. Because eventually we're trying to find a p-value. So our test statistic is what we observed minus what we expected divided by our standard error. Okay? So according to our null hypothesis, what do we expect for a difference between the means? We expect a difference of 0. What is the actual difference that I observe? It's the difference between my sample means. Okay? So the observed difference is x1 bar minus x2 bar. Okay? Notice this is the same thing that we put in the middle of a confidence interval. Okay? This is what I observed, and what I'm expecting is a difference of 0. So, I mean, I can basically ignore this, right? So this looks pretty similar to what we did for two sample proportions, right? Except it was p1 hat minus p2 hat over 0. And then the standard error, it's just the ugly formula that we can't do anything about. And you'll get this down, s1 squared over n1 plus s2 squared over n2. Okay? Not too awful, right? Go through the same process. We get a test statistic. And then what do we do after this? Once we find our test statistic, we look it up in the t-table to get our p-value. Okay? Then look up the t-table. Look up the test statistic. And the t-table to get a p. Yes, we do need a degrees of freedom. And what's the degrees of freedom when we're dealing with two samples? N minus 1, and we use the n of the smaller sample. Okay? So, degrees of freedom, same as before. N minus 1, use the smaller n. Okay? Good, right? Okay? So this is an entirely new thing, but it should feel very familiar, okay? And the key difference here is that the standard error for all of these things is like, it changes when you're dealing with two samples or one sample, when you're dealing with means or proportions. You've got a different standard error in each of these situations. But overall, the concept remains the same. State your hypotheses, make a test statistic, look it up in your t-table, and get the p-value. Okay? And it's just this part. This part is always observed minus expected divided by the standard error, but the way you find your observed, the way you find your standard error, changes from whether you're dealing with proportions or means, one sample or two samples. Okay? And so you got to always keep track of what you're dealing with, and then you'll be okay. Alright. And so all of this stuff only works because we've used the central limit theorem, and so that means we're supposed to check to make sure that our conditions are met. Okay?
Are we gonna have to check on the final?
Yes, there will be a section on the final where you have to check conditions. Okay? It's going to be like the quiz. It's going to be separate from the other stuff. Okay? So the other stuff where I'm going to have you do calculations, I'm going to say the conditions are met to use the central limit theorem. Okay? But there's going to be just one section, or I'm going to give you the thing and I say, where are the conditions met, yes or no? If not, which condition is violated? Okay? Similar to the quiz, okay? Alright, so central limit theorem. Alright, first condition is random and independent, okay? That's the same as before. When you take the sample, it's got to be random or independent, and then you're fine, okay? Actually, the most difficult one to meet, but the easiest one to describe in a problem, I just say a sample was selected randomly. We're good, okay? In real life, sample selected randomly, that's very challenging to pull off, okay? It's like saying, oh, investing in the stock market is easy. Step 1, get $1 million. Step 2, this is how you should invest it, right? But step 1, that's actually quite challenging. So, well, maybe that's not a good example, because you could get started in the stock market with a lot less. But maybe venture capital. Okay. So random and independent. Okay. Number 2, we have big population or large sample, whichever one you want to talk about. Okay. So this one is still the same. Big population, same as before. The population needs to be at least 10 times bigger than your sample. Okay, same as before. So these two, same as before. Three, the large sample condition. Okay, this is the only one that changes. Because before, to check this, you had to do n times p. But now we don't have a p. We only have n. Okay. So this one is that if the population that you're drawing your sample from, okay, so if the population from which you draw the sample is normal, okay, so if that population is normal, then any size n is fine. Okay, even an n of 2, that's fine. Okay, any size n is fine. Any n is large enough.
What do you mean by normal?
Okay, so if the original population follows a normal distribution, okay, if it follows is a normal or normal distribution, then any n is fine. Okay, so if it's unimodal and symmetric, if it's got that nice shape, any n is fine. Okay? If the population is not normal, so meaning it's skewed or bimodal or something weird going on, okay, then you need a larger n. And the rule of thumb is n being 25 or more is usually big enough, or n being 30 or more. Okay, some books say 25, some books say 30. I think our textbook says 30. The other textbook I'm using says 25. It doesn't really matter. Okay, something around there, big enough. Okay. So if the population is not normal, you need a bigger n. Okay, where n equal to 30 is big enough for most situations. Okay. And so these are pretty much the same conditions that we had to check when we were dealing with proportions, and the only one that changed is this large sample condition and how we check for that.
Would we be able to tell this if it's not normal just by reading the problem?
Yeah, I would say somewhere in the problem I'll say the population is normal, okay? Or that the population is skewed or something to tip you off that it's not normal. Okay, how's that?
Good.
Oh, we're 15 minutes early. Is anyone going to complain if we stop now?
No.
I didn't think so. Okay, you guys have a good week.